Up to this point, we've presented some examples of how to solve for the apparent conductivity that one measures at the surface when using low induction number, using instrumentation that's designed with the low induction number relationship. And, as we've mentioned, the terms and the equations that we've seen in this solution turn out to be the cumulative response functions. And the cumulative response function we see over here for the vertical dipole is defined as the integral from z1, in this case down here just pictorially, z1 to infinity. So whatever z1 is, whatever the depth divided by the intercoil spacing is for the first interface, that integral is equal to the area from z1 out to infinity. So that corresponds to this point on the RV of z curve over here for these different values of z. So the question that we posed the last time was, okay, we know that a layer, let's say the second layer, between z1 and z2 will contribute to the apparent conductivity in proportion to this area under the relative response function. So the question is, okay, how do we get this? How do we get this area between z1 and z2? And of course, you could just do the integral of 5e of z from z1 to z2. That would be one way to do it. However, what the approach that McNeil outlines for us, because it turns out to be much simpler than doing that integration of phi, between limits of z1 and z2, it's much easier to calculate RV of z from z1 to infinity of 5e of z. We know that that's 1 over 4z squared plus 1 to the 1/2 power. And then to manipulate these RV of z's. So if we get RV of z1, we get this area. If we get RV of z2, we get this area. So the question is, okay, how do we get this area between z1 and z2? Well, we just express that area as a difference in the r's. And, I think you're already getting the hang of this. So we have a relative response function. We have this area we're interested in. We know that the layer between depths z1 and z2 contributes to the apparent conductivity measured at the surface in proportion to this area. And that area is just equal to the difference in the cumulative response functions. So pictorially or visually, graphically, we are just, we have an RV of we have this RV of z1, or R1 as we've been calling it, this RV of z2 or R2. We're just subtracting RV of z2 from RV of z1, which means, visually that we're just taking this area away from this area up here to get this area between z1 and z2. So the difference in these two response functions gives us the area between z1 and z2 under the relative response function. So all we're doing is just subtracting R2 from R1. So here's another question for you. We've got a little bit different looking area. We're going from the surface down to the top of the layer. What is this area? How would you express this integral as a difference of cumulative response functions? Well, we know this area is equal to R1 minus R2, right? But R1 is, Z1 is equal to 0, right? So, okay, well, RV of 0, the cumulative response function for z equals 0 is just the total area under the curve, which happens to be equal to 1. RV of z1 is just the total area under the curve from z1 out to infinity. So if we subtract this from this, we get this. So this area from 0 to z1 is just rv of 0 minus rv of z1. And of course that's also the integral from 0 to z1 in this particular case. So since the total area under the curve for z equals 0 of the cumulative response function for the vertical dipole is equal to 1, we get that relationship. We get this weighting factor that you've seen a couple times now, just 1 minus r1, as we've been kind of using a shorthand notation for it. So just in summary then, and I think this is a bit redundant, but just to make the point, we figured out how to compute these different areas in terms of the cumulative response function. We know that the apparent conductivity that we measure at the surface here is just the sum of the total of the contributions from all layers, and that those individual contributions correspond to the conductivity of a given layer times the area under this relative response function, which turns out to be a difference in the cumulative response functions. And in visual form again, sigma 1 contributes in proportion to this area, sigma 2 in proportion to this area, sigma 3 in proportion to the remaining area. In this case, this is the bottom of the model. And in mathematical form, these areas again are just 1 minus r1, r1 minus r2, and r3. So we've already used this equation. We did a 3-layer problem. We worked through it. I think you, at this point, should understand the nuts and bolts behind these cumulative response functions, why the weighting factors take on the form that they do, 1 minus r1, r1 minus r2, and r2. This would be in our simplified form down here. And so the next time we're going to present an example problem that will show you how the detection depth, or the depth of exploration, can actually exceed 1.5 times the intercoil spacing. This rule of thumb, 1.5 times the intercoil spacing, is often used as the depth of investigation. You might, if you had a particular problem that you were considering, say, well, okay, if I'm using the EM31, if my zone of interest is below 5 meters, then I shouldn't be using the EM31. But you may, in fact, be wrong about that using this simple rule of thumb here. And we'll show how that can actually turn out to be the case. So talk to you next time. Thank you.